So, yesterday's class we have started initial discussion about bending stress. Okay. So today we will discuss it in more detail about bending and shear stresses in beam. So now you see bending and shear stress in previous class, yesterday's class, I have spoken about a typical case where the pure bending condition is coming. So what is pure bending? Can anyone explain what is pure bending? Yes. So the portion of the beam after loading where the shear force becomes zero, however bending moment remains over there. Okay. So that condition of beam will be termed as pure bending condition. And a typical pure bending condition, if you see, that is yesterday we have seen that if we take a simple supported beam, something like that, so it's a simple supported beam, and at an equidistance two loads are being placed. So let's say at a distance A from both ends, the loads are placed. So if I take a condition like this, then you can get a typical bending moment diagram which will be trapezoidal in shape like this, and the bending moment value over here will be P into A, and it's a positive bending moment, right? And on the other hand, if you see that shear force diagram, then for this portion of the block, yesterday we have understood this, right? So there is a positive shear and there will be a negative shear on the last portion of the beam, whereas for the other portion of the beam, this much portion, that is from here to here, this portion of the beam, you can see there is bending moment is happening. There is a typical amount of bending moment, however the shear force remains zero. So this is actually what is called a pure bending condition. Okay? In many other cases also you can achieve pure bending condition. Although you can see that pure bending condition is not always be coming in your beams, right? Because there will be some kind of shears, but you can see in case of most of the cases the shears will be more at the support region, whereas the bending will be more in the middle region when it is a simple supported kind of. Okay. So considering that, if we take the case, so you can see that the middle portion of the beam CD, that is this portion, as you can see, the moment is PA, which is uniform. The moment is uniform. However, there is no shear. This is actually pure bending condition. Clear? Now, considering the pure bending condition, let us try to find out what is bending stress. So, what is bending stress? Bending stress is the stress which is generated because of the pure bending. Okay? So, to investigate the state of stress produced by pure bending. So, when the beam is under a pure bending condition, at that time, the deformation which is taking place within the material, that needs to be studied. Okay? Why you need to study? What is the importance of studying bending stress? The bending stress needs to be studied because you see every material will have some amount of bending resistance, and the materials will be failing under the stress condition if it exceeds the allowable stress condition. Okay? So, to restrict the material behavior such that it does not fail, okay, you need to investigate the bending stress condition inside the structure or inside the beam. Clear? So, the first step to understand, you need to understand few relevant figures for this. After that, we will get into the derivation of the bending stress formula. Okay. So, the first thing you see, you can see before deformation, if I take a cross section of the beam, yesterday I have shown you, it's a cross section of the beam, this beam, if I take this beam, simple supporter, if I take the cross section of the beam, and or I can say the longitudinal side, if I see from the front, then I will be seeing the beam something like this. I will be seeing the beam something like this. And it is a rectangular cross section, so cross section of the beam will be something like this. So this is my front view, and from side if I see, I can see this. Correct? So this is my cross section. If I cut any section, any position over here, I will get a cross sectional view of this. Correct? So this beam, when I take, when there is no load inside the beam, then what is happening? You can see lots of lines are there. These lines are layer by layer kind of things. Okay. So let's say layer by layer of materials. Okay. And you see, before the deformation, if I consider each layer as a fiber, okay, fiber of material, so each layer will be a straight line. That means there is no deformation. Correct? Now, when this loading condition comes into the beam, so now if I load this beam with this PB load, right, and if I investigate that beam, so what will happen, you see, after the deformation, it takes the shape something like this. So there will be a bending kind of things coming in. Correct? So where this phenomena will occur? The predominantly this phenomena will come in between this portion. This is under pure bending. Correct? So there is a bending downward. So there is downward bending. So you see this fiber is getting extended. Isn't it? This was a straight fiber. This horizontal fiber is now getting extended. Isn't it? It's getting extended. So extension means it is under tension. So the bottom fiber comes under tension, and the top fiber, which is this one, you see, this is getting shortened. That means it is under compression. Have you understood? So top fiber will go for compression, bottom fiber will come under tension. This is a pure bending case when we are considering simple supporting beam. However, if I take a cantilever bending case, then you see it may be reverse condition. The top fiber will be under tension, bottom fiber will be under compression. Suppose I take a cantilever beam. If I take a cantilever beam something like this, then how does it bend? It bends something like this, right? It bends something like this. So when this bending is happening, then your top fiber becomes under tension, bottom fiber becomes under compression. This is the reverse. However, the bending phenomena will remain same, right? The space generated will remain same. Okay? So now you see, after deformation and before deformation, if I see, then you will observe, typically if you observe, and there are some assumptions behind it also, those assumptions we will understand later, but if you see this EF fiber, which is nothing but a fiber which is passing through, let's say, the middle portion of the beam, if it is a rectangular section. That means I am considering this point and I am considering a section, a line along this. Okay? So if I consider a line along this, then the fiber which is remaining at the middle of the section, in case of a rectangular section, please try to remember this. Why I am saying it's the middle of the section? Because it is actually, we will be seeing that it will be the section which will be passing through the centroid. Later on we will understand. Okay? So if in a rectangular section, if I consider, then the section which will be middle of the section, that is actually the centroid. Correct? So if I take a fiber here, let's say, so if I take fiber here, so what we will observe EF fiber? So if I observe the length extension of EF, we will typically observe that there is not extension happening for the fiber which is passing through the centroidal. Have you understood? And this is the typical phenomena where we will be taking some assumptions also behind it, And this not extension of this after the bending, that plane or that axis will be typically named something. Okay? We'll come to that. However, you must understand that there will be a plane or there will be a section. So you see, there is a plane. So if I cut this beam in between, and if I do it like this, if I cut it in this way, horizontally, if I cut it like this. So if I cut it like this, there will be a plane coming, which will be looking something like this. It will be a rectangular kind of plane, and in that plane, in the middle, you will observe that there is no extension of the fibers happening. Okay? And that surface will be termed as neutral surface. So there is no extension, there is no elongation, there is no shortening. Okay? So that surface remains neutral because of the loading condition which is coming from the external loads. Clear? So that neutral surface that will come into picture when we will be understanding our bending stress theory. So above the neutral surface, what is happening? Above the neutral surface, what is happening? Compression is happening. So there is a bending stress. So there is a stress getting generated which is compressive in nature. And below the neutral axis, what is happening? There is a tensile kind of bending stress getting generated. Okay? And what is happening at the neutral surface? There is no stress. So you can understand. So there is a variation of stress from the top to bottom, and typically the variation will see that variation will be becoming a triangular kind of variation. I'll show you. Okay? So at the neutral axis it becomes 0. So there is no bending stress at the neutral surface or at the neutral axis. Okay? Now developing this theory of bending stress, we need to have some assumptions. What are those assumptions? The first assumption, you can see the beam is prismatic and it has an axial plane of symmetry which we take as XY plane. It should be symmetric. There is an axial plane of symmetry. And prismatic member I have explained earlier. Okay? Cross-sectional area is not changing, right? So prismatic. The applied loads also act on this plane of symmetry. So there is a plane of symmetry, and the applied load is acting on that plane of symmetry. Okay? Therefore, bending only takes place in this plane. That means, if I load it vertically, bending will happen like this. It will not happen bending, it will not happen that bending is happening like this. Means, slab से लोड आ रहा है, बेंडिंग किधर हो रहा है? डाउनवर्ड. सो जो प्लेन से लोड आ रहा है वही प्लेन में बेंडिंग हो. The blending is happening in the same plane. It is not happening, bending is not happening in the out of plane. That is a different concept, okay? Out of plane bending. So it is not happening that laterally beam is buckling like this, bending is happening. So in the same plane the bending is happening. This is another one assumption. The third assumption is a very, very important assumption which is not at all true, you can say. Which is not at all true, but we are assuming. That is, material is homogeneous and isotropic. In most of the cases you will see concrete, homogeneity, getting the homogeneity of concrete is very difficult. You cannot say everywhere the concrete is same. There will be some kind of difference. To some way, when you design a steel structure or you are getting some material kind like composite fibers and all, composite structures and all, then you can say the material is homogeneous. But concrete, say, we are assuming that material is homogeneous. We are assuming that it is isotropic. Because to most of the extent, it will be considered as homogeneous. So, assumption here is material is homogeneous and isotropic. The fourth assumption, very simple and very important assumption, that material obeys Hooke's law. What does it mean? That means we will be studying everything within the elastic limit. That's all. Correct? Next assumption. The modulus of elasticity. Very important. Very important assumption. If this does not happen, the modulus of elasticity in tension and compression is same. Elastic modulus on the tension side and on the compression side, because of the tensile loading and because of the compressive loading, it is remaining same. If it is not same, then you cannot have that kind of behavior where from top to middle same stress variation, from bottom to middle same stress variation, and at the middle it is zero. It cannot come. Because if strain is same and modulus of elasticity is different, then what will happen? Stresses will be different. Right? So the elasticity, modulus of elasticity for tension side and compression side, they are remaining same. Next assumption. The part of the between E and F, the part of the beam between E and F, EF, okay, takes the form of a circular arc. This is another one very, very important assumption. Okay? So if I cut a beam which is under pure bending condition, if I cut it after the loading, you will see a circular kind of arc is coming. And on that arc, at the middle portion of the arc, middle portion of the section, the no extension will be happening for that section. Okay? Last assumption is, in this deformed configuration, each cross section originally plane, very important assumption, originally plane remains plane and remain normal to the longitudinal fibers of the beam. Very simple way, the plane section remains plane after the bending. That means what is happening? If I am taking any section, the section will remain plane. It will not be getting distorted. Distortion will not happen. Okay? So if distortion happens, we cannot study properly. Okay? So plane section remains plane after the bending. This is another one very important assumption for bending fluid. So this is what we have already discussed. As a result of deformation, what will happen? The convex side of the beam gets elongated and concave side gets shortened slightly. Somewhere in between the top and bottom of the beam, there is a layer of fiber which remain unchanged in length. That's what I have explained, right? Somewhere between top and bottom, there will be somewhere a position. It is not at the middle. Please understand this. It is not always at middle. If it is a rectangular section, then it comes under middle. But it not always that section where there is no extension or unchanged in length will happen. It will be coming at the middle point. Okay? The surface where this extension is not happening, that surface will be termed as what? Neutral surface. And the intersection of the neutral surface. So this is your surface, right? This is your surface. Okay? And the intersection of the neutral surface with the axial plane of symmetry is called the neutral axis of motion. So you are having this neutral surface, you are having this plane. So this axis will be termed as what? Neutral axis. Okay? Is it clear? Have you understood all the assumptions? So 2-3 assumptions are very important. One is homogeneous isotrope. Second one is obeying the Hooke's law. Third one is plane section remains plane after the bending. Fourth assumption, after deformation it takes the shape of circular arc. Clear? With this assumption, let's move to the next part. How to find out bending stress. So if you see, it looks like a very typical mathematical derivation, but very simple. It will come from geometry only. Okay, it will come from geometry. We will understand. So what to understand? You see, we have said that at time of pure bending there is a deformation, and because of the deformation there is a circular arc getting formed. So if there is a circular arc getting formed, it will be getting joined at some center point diagram. If there is you understand what is the arc? So if I am having a circle like this, so there is a center, correct? And circular arc means if I take this point and this point, so if I cut it over here, so this is an arc, right? This is an arc. So it will be having some center. So this is what is the center point O. Okay, and the beam after bending took a stage of kind of travel. You understand? This fiber extreme out is under compression, extreme bottom under tension. Okay, and you can observe there is an axis CD. Okay, in between somewhere this extreme out and extreme top and extreme bottom. Okay, which will not be getting elongated. That is what is our assumption, right? Now considering that, let's take a portion of the beam. We are taking a portion of the beam and CD which is under pure bending. So from that previous section pure bending, we are cutting out some. Consider two adjacent sections MN and PQ in the portion CD before deformation. So let's say before deformation, so this is my CD part and I am having two planes, let's say MN and PQ. It is separated by very small distance dx. Have you understood? Very small distance dx. So two vertical things I am putting MN and PQ. Correct? So before deformation, what is happening? This is separated by this. So they will remain straight, right? They will remain straight और टेढ़ा हो जाएगा. क्या कैसे रहेगा? Before deformation, it will remain straight. Correct? After the load is being put, bends. So there is a circular pattern comes. So after that, what happens to this MN and PQ? What happens to this MN and PQ? So if I take MN and MN, you see this MN. If I take this MN as reference, then you see PQ will be little bit getting distorted, right? It will come little bit distorted, right? So if I take this PQ as a reference where the distortion is happening, so you see now when the transverse load acts at the and the same portion is under pure bending, which is uniform, it is reasonable to assume that bending in deformation will be also happening uniform. Okay? So after deformation, CD portion will take a shape of circular arc. This is what is happening. Circular arc is coming. Clear? एक के बाद एक समझिए. So this CD portion was straight. This CD portion is becoming a circular arc. Subjected to what? Subjected to pure bending. And where from? So these are the bending. So both sides there will be M coming. It is not M plus delta M. Please understand. Why both sides M is coming? Because we have seen that P into A, bending remains constant. There is no CR and bending remains constant. That is what is pure bending, right? And we are assuming that pure bending condition is happening and assuming that we are deriving that. So both sides you see the bending moment M is coming into it. Correct? Now this is the section which is before and this is the section which is coming after. Now you see, let us consider that after deformation, the planes of two adjacent cross sections MN and PQ intersect at O. So after bend, okay, after bending, so in this circular arc, after bending, so initially it was vertical, then there is a bending, so it intersects at point O because it is circular. So you see MN and this is your PQ. Can you see? This is your PQ. These are attached at a point O. Clear? Geometry, simple geometry. Let us denote the angle formed by the two planes after deformation is D. So you see, this is your MN which is getting extended to O. This is your PQ which is getting extended to O. And the angle between this line and this line is D. Got it? Now, if the curvature of the neutral axis, so which one is neutral axis? You can tell. So can you name which is CD? So CD is the axis which is passing through the some point where there is no bending stress coming. That means what does it mean? CD does not have any extension. Correct? That is what is assumption. So CD, if it is neutral axis, then you can see this is your radius. So what is your radius of curvature? So radius of curvature will be 1 by radius. So 1 by rho. Correct? So radius of curvature is denoted by this line. So radius of curvature of the neutral axis. Please understand. Radius of curvature of the neutral axis we are considering. So radius of curvature of the neutral axis is 1 by rho. Correct? Now, abhi geometry mapping. So now you see what will be the value of d theta? What will be the value of d theta? So if I take this is the dx. So please try to understand very clearly. This is coming from geometry. So this is your mn. This is your pq. So between mn and pq, what is the length? Dx. So at the neutral axis level, what will be the length between mn and pq? Dx. Because it has not extended. Other places it will extend. But at the point of neutral axis, it will not extend. So that's why it is dx. So you see, in this neutral axis, we have taken this length as dx. Right? So dx is equal to d theta into rho, I can say. Dx r d theta. R, length of the arc is equal to how much? R into d theta. So this, if I take this is my radius and the other one is my radius of curvature. So this is my radius rho, right? So if this is my radius, then this dx will be equal to how much? D theta into this is rho. So that's what I have written. Dx equal to d theta into rho. So that means d theta is equal to dx by rho. Got it? Simple equation, nothing else. So what will be dx by d theta? Dx by d theta will be equal to 1 by 2. So one equation we have established. Dx by d theta is equal to 4. And what is dx? Dx is the distance between two perpendicular sections at the neutral axis level before deformation and after deformation, which is remaining same. Huh? Triangle law? No triangle law. This is arc. If I take a circle, I take r. This is r, radius r. The arc length, if it is s, and if it is theta, then s equal to r theta. Correct? If the angle theta is very small, then s equal to r theta. But this is coming from circle equation. Okay? So no similar triangle, nothing else, nothing coming. Similar triangle may come later. Let's see. So now you see, if a line P dash Q dash is drawn, can you see P dash Q dash? And through what it is passing? You see it is passing through a point which is at the neutral axis level, and that point is termed as B. Okay? So if a line P dash Q dash is drawn through a point B which is parallel to MN, that means I am drawing a line which is parallel to MN. Because you see, after distortion, PQ has changed its length. So I am trying to draw a line which is parallel to MN. What does it mean? Parallel to MN means I am producing this PQ. So I will get the extension. Parallel to MN, before deformation, parallel to MN. So it is PQ. So I am drawing a parallel line to MN, which is P dash Q dash. So from that, what I will get? I will get the extension amount. Where? At the top level, at the bottom level, or at any level. Here I can find, here I can find, here I can find, here I can find, here I can find. Any level I can find the extension. Have you understood? Clear? So now you see MN, which indicates the original orientation of the cross section. What is original orientation? This is your original orientation. Correct? So from the original orientation, we are going back to the original orientation. So this is actually, if I vertically drop it, you see, it will touch PQ. If I vertically drop it, it will touch theta. Correct? So I am going back to the original orientation. So original orientation से deviation कितना हो गया? P dash. Original इससे deviation कितना हो गया? Q dash. Clear? So now, if you consider that, then the segment CD dash. So you see, CD dash. Here comes the point. That is what I said. That you should not only concentrate on this fiber and this fiber. Rather, your concentration will be on each and every fiber, because you may need to find out bending stress amount at any point inside the beam. Not at the extreme route or extreme length, extreme top fiber or extreme bottom fiber. You may have to find out at any point in the beam. So any point in the beam section, if you want to find out, we are considering a point, let's say this D point. So this D dash, so you see D dash is the extension. D dash is the extension. And here whatever symbols we are using, those are very, very important. Okay. So D dash is the extension. So now let's say this D dash point is at a distance y from the which position? This y we are drawing as which position? This y is from which? Neutral axis CD, right? So this D dash is the extension at a position which is at a distance y from the neutral axis. Same thing I can do for the top portion, right? Same thing I can do for the top portion. So if I take this as positive y, इसका ऊपर से करेंगे तो क्या होगा? It will be negative y. Correct? Have you understood? So if I take tension as positive, compression will be negative. Sign will change. Correct? So now, if d dash is the extension, so what will be d dash? So if I apply the trigonometry tan theta, so if tan theta is very small, theta is equal to tan theta is equal to theta. So that means what will be the value of d dash? So d dash will be equal to y multiplied by this angle. If you come from geometry, this angle again will be equal to d. If you come from the geometry, if this is from this to this, if the angle is d theta, if between these two also the angle will remain d. Okay? So your d dash will become equal to y into d. This will come from geometry. Clear? So d dash is what? Now you tell me, what is d dash? d dash is the extension where at a distance y from the neutral axis. For what? The fiber which I am considering. Correct? Which location? At the bottom of the neutral axis. Correct? Is it clear? So considering that d dash equal to y d theta. So now original length कितना था? CD. So what is the length? dx. So original length was dx. So what is the extension? What is the extension? d dash. d dash. This is your extension, right? Original length was dx. So d dash by CD dash, it will be the straight. Understood? Basic fundamental math. This was my original length, right? What is the extension? Initially when it was horizontal, at this level, what was my CD? dx. It extended by how much? d dash. So original length, extension divided by original length will give you what? Strain. That is what is strain. So strain is coming, and strain is d dash by CD dash. So d dash we have derived. What is that? Y dx. Right? Now you see, I have replaced this d theta dx with 1 by rho. So it is becoming y by rho. So you see, what is the value of strain? strain will become equal to y by rho. And what is y? Y is the distance from the neutral axis. And what is rho? Rho is the radius, or 1 by rho is the curvature of the curved portion. Clear? Up to this it is clear? Now next you see, what is stress? Stress is modulus of elasticity multiplied by strain. That's what we have done. Stress equal to E multiplied by epsilon x. So, what is epsilon x now? Y by rho. So, is equal to E multiplied by y by rho, which I have written in this way, E by rho. Because you see, E is constant, rho is constant. Right? Because curvature is not known to vary. So, y is the variable. So, now you can see the relation sigma x becomes E by rho into y. So you see, this shows that the fiber stress, what does it show? It shows that fiber stress due to pure bending vary linearly with the distance y from the neutral surface. Have you understood? Because E is constant, rho is constant. So if I take this part as constant, what is this equation becomes? It's the equation of straight line. Sigma x equal to, you see the equation is sigma x equal to what? Sigma x equal to E by rho into y, right? So if I take this as x, let's say, sigma x को अगर x ले लेते हैं, तो ये constant हो गया, तो c into y, so x equal to c into y or y equal to c into x. What is the equation for? It is the equation for straight line. Y equal to mx plus c, right? So this c is nothing but, or I can say this is nothing but my my, okay, or y equal to mx, whatever it is. So it's the equation of straight line. It becomes equation of straight line. So the variation will happen what? Variation will be straight line. So the stress variation from the neutral axis to the extreme bottom fiber, as well as stress variation from the neutral axis to the extreme top fiber will be linear. And what will happen at the neutral axis level? It will be becoming equal to 0. Correct? In next slide we will be seeing how does the stress variation will look like. So have you understood the stress variation, why it is becoming linear? Got it? Next you see, if the fiber on the convex side of the neutral axis is considered, the distance y is positive. I have told you that y, when I am taking bottom, I am taking as positive. Different books have taken different convention. I am following Timoshenko's books. So from Timoshenko's convention, if you take that bottom fiber from the neutral axis, I am taking positive, and the top fiber from the neutral axis, I am taking negative. Okay? So convex side means this one, and concave side means the other one, right? So that way, positive, negative sign you can take. So considering that, finally, if you see the stress distribution of the what is called stress distribution from the neutral axis, as we have seen that because of the pure bending condition, the equation of the pure bending stress, that is sigma x, is equal to E by rho into y, and it is a linear variation, and the linear variation is happening from the neutral axis to the bottom and from the neutral axis to the top. So you see the typical stress variation of bending stress throughout the depth of the beam. This is the depth of the beam, right? This will happen like this. So at the extreme-most top fiber, this will be like this, and then gradually it will reduce and it will come to zero at this point. On the same way, for the bottommost portion, it will be maximum and it will gradually reduce and come to zero. This is what is the stress variation in case of a beam under pure bending, and this is what is bending stress. Have you understood? What's the time now? Already time. So I could not finish. Tomorrow's class or day after tomorrow I have a class. So there we will be explaining the further thing and finally concluding on this bending stress. Okay? And then we will go to shear stress derivation. Clear?
Thank you.